Yeah, so today's lecture is based on digital logic, and the textbook says William Stoll's Computer Organization and Architecture, the 10th edition. So, yeah. So today I will go through about some logic gates. So what we are cover is gates, digital logic gates, and logic gates. And algebra, conventional logic circuits. Right. Logic gate, Boolean algebra, and combination logic circuits. So those will be covered in this tutorial. And today we will discuss about logic gates. So so I will just quickly go through about the content. So yeah, we will learn about these gates, simply not gate and gate to gate, and some of Boolean algebra and what are the circuits. Yeah, use of NAND gates. Yeah, these will be discussed today. So basic logic operators. So in logic is what are the gates that you aware of, students? So that the gates, what are the gates you aware of? You can text me if you like, or others. Yeah. Darsh, scan and gate or gate and not gate. So, what are those actually? Is it and gate or so? What are those? What are the tasks in logic gates? In similar, we say bar the door. So probably in areas, I think you need to design some of the gates actually from using the knowledge of electronics, right? So we do not need to go that far, but what we need to do, we need is the idea or the theory behind these gates, right? So what we can mean by logic gates. So we'll go through with those syllabus. So basically, you need to learn and gate and O, not, and so on. is exclusive of this O. So something similar to this. So R and then operation. And next. So 2, 3, 4, 5, 6, 7. So these 7 gates are included in your syllabus. So first thing. So what is the logic gate? The logic gate. Anyone? So I can explain this way. So let's take a simple gate, not some simple is this. So we need to connect this. So this is not gate. So idea is for that in gates there are inputs and outputs. There can be many number of input for a single gate that can also be done. But however, there will be only one single output, right? So if there are three lines, then you can say A, B, C, and this will be, let's say, F. So here there will be yeah, for NOT gate there can be only one input because we cannot do any we cannot do any operators. So for NOT gate it will be only one input. Let's say A, then this is A bar. That is, and we can say it is not A, right? For O gate, in this gate there can be many input. Let's say even three, A, B, C. Let's take A. This will be A plus B plus C. So you can see this. In gates there are inputs and outputs. The input, yeah, when we consider the output will be based on the logic or maybe a rule that will tell how the input will be derived. So that will happen in logic gates. In another way, there are set of rules uh, regarding each of these gates, and we can derive how will be the output with corresponding to the particular input in the given time. So that will be logic gates, right? So we need to go through each one. So first one is and. So and this, which we can say we'll do dot operator in Boolean dot operator or the same thing, and we write down this using this symbol, same operator. So that means let's say B will be equal to A and B. Right? The symbol is here, straight line, and something similar to this. So if we consider it has two inputs, let's say this. Right? So this A, B, C, and the output will be simply we can say AP. Even we can remove this dot and simply write this two like this at AB. So it means A dot B or A and B. Right. So let's consider about the truth table. Is AB. So when you derive the truth table, I think you have your A-levels memory. We need to go through. So it's like this. So there are two inputs. So how many occurrences in the truth table? So there will be 2 to the power n inputs. If n inputs, the output, the number of rows in the truth table will be 2 to the power n. So here is 2. So 2 to the power 2 is 4. So there should be 4. So 4 divided by 2 is 2. So then 2 zeros and 1 1. Then again we can divide this 2. So it means 1. So 0 1 0 1. So these are our 4 occurrences. So here this is also 0 and this is also 0. So our logic is if both inputs are 0, then the output A dot B, A and B. So it also 0. The logic. And for this one. So B is 1. So even that AB will be 0. For this one also 0. Only it will be true for if all the inputs are true, then the output also true. So that means we need to do both these inputs, then only the output will be. That's how the dot operator works. So do you have any questions? Some of you have mentioned. Yeah, can you able to send me an email regarding your request? Then yeah, I will extend to next week. Please send me an email. We need to have a formal request as well. Right. It's about and it's will quickly go through the next gate. So that is O. So please write this down. Right. So operator is this plus in Boolean or in logical way. the operator we derived this symbol, and it is this. There should be a curve in the beginning. A plus B O A O B. You can say that means A plus B also equivalent to A O B. Right. So what is the logic or what is the rule? So we can quickly derive it by using the truth table. A plus B. So if the both is 0, that means 0 plus 0. So output will be also 0, right? So if either one will be true, let's consider E is true, then 0 plus 1. So that is 1. It will be 1. And here also 1. And this is the tricky point. Actually, this will not be tricky since you already know. So 1. Here not actually 1 plus 1. It's 1 or 1. So 1 or 1 is always 1. Because the both inputs are 1. So it's 1. So it's like you can write in this way as well. 1 over 1. Right? So in the combinational logic circuit, you will going to do the binary addition as so in that binary addition. So this is will be in for a future. This binary addition. In binary addition, that means 1 plus 1. Now this is the summation operator. And that means we are adding those two. So these are binary. That is binary means only 0 and 1 will be there. So what is the addition of 2 1? Anyone? So in binary addition, what we can see is it's 1 0, right? So 1 plus 1 is 2. 2 can be represented the binary form in this way. So this is 2 to the power 0. This is 2 to the power 1. 2 to the power 0 is 1. 1 into 0 is 0. 2 to the power 1 is 2. 2 into 1 is. Right? So this is binary addition. But this is the override. So don't get confused about this. Right. So our next gate is not operate. So next operator will be derived or writing this way. So in Boolean algebra, it is this. So in Boolean algebra, this is and mathematical logic will be this. And when we are working with symbols, we can simply say this way as well. This is not A or A bar. It's also equal and the Boolean not A and then A dash. These all are equal. So there are many number of ways you can write the not operation. And the gate will be this. There should be small round here or small circle. So the input is A, the B, A bar or not A. Fine. So there are only one input, so there will be only two rows. A, the output will be A bar. So means it is 0. Not 0 is 0 or 0 bar, it will be 1. Is 1, then it will be 0. So this is the bar not operator. Right? If you have any problems, please ask. So the next operator is XOR. Operator is something is the symbol. The operator, and we can write in this way. A XOR B in the circuit. A B, this is A or B, right? Here we go 1 0 1 0 1. So what is the logic in XOR gate? Anyone? What is the rule or logic behind the XOR gate? No one knows. It's something like this. So in XOR gate, the logic is either one input should be different with other, right? So that means if both are equal, both inputs are equal, then output will be for these two, 0, 0 and 1. If both are equal, the output will be 0. Here and in other case, it will be 1. Right? That is the logic. Logic is either one should be different with the other input. If this is true, then this should be false. If this is 1, then this should be 0, like that. And please let me know if you have any questions. So probably you have already learned about this in your A levels. So now I'm going to the norm gate. This one. So what is the symbol for OR gate? Symbol is OR gate is O. Simply you can draw this as so this is the our OR gate, right? And no is O into not. So not gate is this, right? So now we are connecting to logic circuits A, B. So what the answer here? A plus B or A or B. So now we are going to negate the whole thing. That is A plus B not. Right? A plus B. B or B going to negate. So A plus B. So it's only this will be 0, other all three occurrence will be 1. So into not. So that is if 0, this is 1, this one is 0. Okay, since it is 1 is 0 and 0. So this is the truth table. And what we can do is we can simply since this is a simple gate, we can reduce it to this way. In digital logic, we are defining the not operation by including a simple circle in here as well. So like in not gate. So this is how we are defining the flow of the current direction by using a triangle, and simply we are putting a zero. So indicate this will be negative. So here also we can do that. AB. So this is operation, and we are negating this operation, and we are negating all things. Right? And so I will explain in the Boolean algebra also. We can simplify this. That is by using the De Morgan's law, we can simplify this into A bar dot bar. So the not operation will be going to each inputs, not for the whole thing. By using the De Morgan's law. Right. So this is no. So operator will give A plus B whole thing negation. Right. So we can simply take this way as it or the whole or the is equal as this whole line. Please let me know if you have any questions. So what is and is A dot B, and we are negating the whole thing. That is this, right? Or simply A B whole thing not A B not or right. So what is the gate? Simple. We are doing an and we are getting the A B. This is A B not. Simply this. So what is dot operation for both zero? So again 0 and into not is 1. 0 and 1 is 0 and again 1. 1 0 is A dot B will be 0 and we are going to negate that is 1. And here it will be true for A dot B and we are negating, so it is 0. Right? With the NAND operation. The logic is we are doing the AND operation and we are negating. Yeah, in De Morgan's. So we are using De Morgan's law. This will be equal to A bar plus B bar. De Morgan. So the final case. So I think you can do so I simply do that X now. So it is don't consider this is X now. So this X it is the not operation of XOR. So we can write it this way. So we can simply pronounce X now. So what is XOR bit? XOR B. And we are going to negate that. So this is the same. XOR B, that is, and same as previous, we are putting on in front of the gate and A. This will be A. So B do not. So you may aware in previously we use XOR gate. So there should be different output to true. So in this way it should be the same output is both outputs are equal. That is, if both are 0, 0 or 1, 1, then it will go into true. And if those are different, then it is 0. This is the logic here. Right. So I think you need to aware of these gates and the symbols and how to derive the truth table. So if you have questions, you can ask. And now one simple thing. Yeah. So there is another symbol that I told you, it's the current direction. This. So there is another old buffer. So that is this A. Then it's also A. So it is the same output. 0, 0. So it also A. The input is 0, 0. The output will be also 0. If it is the input is 1, the output is also it's all buffer. Okay. So do you have any questions up to now? Now we are going to do again by combining these logic gates. We are going to draw gates, multiple gates for getting a single output. So there that means there can be multiple inputs, right? And so my first task, try to draw a gate to get the summation of three inputs, that is x, y, and z. Please draw a gate and put into the chat to get this answer. X into y into z. You need to get the summation or do the logical OR for three inputs. So inputs are x, y, and z. So what is the gate? Or what is the logic circuit? Okay. One of you, thank you, Darshan. O gate with three inputs, right? So that is this. So O gate is this. There should be one output. Consider this is F. The output F equal to x plus y plus z. And Y inputs x, y, z. Right? You can see B. Right. Then yeah. Thank you, Mithili. Your answer also correct. And the next question. So draw logic circuit for this one. So output is x will be equal to a plus b into c. A plus b into c. Please draw the logic circuit for this equation. So to get this output, please derive the logic gate or logic circuit. OR gate for A and B, output will be A plus B, and that output can C should be connected through an AND gate to get the final output. Right. So we can do that. A and first A plus B. So we need to foundation. So plus B is O. So B A O B and get the connection C. And C C is will be with that and so is A plus B. So we can so we consider this. So this should be equivalent to this aspect. We know the operation of these gates are correct. So these two should be equal. Actually, these two are equal. Right. So another task. To O B dot C B and C and think of. So what is the logic circuit? So draw the logic circuit for this equation assay. So please draw the logic circuit for this equation. No, simple, right? So A and the so what we this connect all the A plus C we don't see and then big bar. Right? Yeah, Harita, your answer also correct. A like we use that when you are deriving the logic gate this way. And a, you are not correct, put the dot inside here. If you have put the dot here, then you can simply go through and only the lines are interconnected where this dot is happening. If you don't put that dot, you don't put that dot, and you simply draw a line this way, that means it will connect here and here also. To avoid that, what you need to do is you need to show it's not going to connect. How we can do that? By doing this again. It is started from here. We need to put the draw this way. But however, if we write in this way, that means it will only going to connect to this line. Right? I think it will be very easy for you to draw any diagram. So, did you ever if 7,400 in this chip? It has actually 4 NAND gates. That's actually 4 NAND gates. So you can search through in the internet to check whether how those NAND gates are connected. By searching through the chip code is number 7,400. So our next topic is reducing gates. So it can be done now by using the algebra, logic algebra, and even you can simply uh, draw any gates. So let's consider about how to draw with a less number of gates. Consider output A into B plus B. Right? So if you aware of Boolean algebra, so B dot B, B dot B will be equal to B. Right? So that's from the Boolean algebra. So it means A dot B. So however, if we need to draw this exact diagram, exact circuit, so it can done by this A B. E dot B is that is here also B and here also B. Right? It will be B dot B into A. A B. Well, here see the other connection. Right? So this will be very helpful. Right. So as I mentioned earlier, 7,400 it has four and has four. So that means uh, basically no one net gates are used in very often, and and then no, those are considered as universal gates. These NAND gates, NOR gates are considered as universal gates. What that means is we consider the function behind these gates, that is uh, so NAND gate is a and into n. So we can derive any other function, that is even we can derive NOT gate, AND gate, and OR gate. All three gates can be derived using only NAND gates and NOR gates. So that's why we call these NAND gate and OR gates are universal gates. So let's consider how to derive the NOT operation, NOT gate, by using only by using only NAND. Since it's a universal gate. So what is a NOT gate? So it should be only one input, and the output will be about 0, 1, 1, 0. Right? So NAND gate is NAND gate. Right? So there should be only one input. and usually we are connecting at least two input for NAND. So this is A, and here also A and A. So what is this? A dot A, A dot A into bar. So when consider Boolean algebra, A dot A is equal to A and A bar, right? So A, and we are getting A bar. So this is how we can derive the not operation here in this connection. This is the connection now for these two lines. Right. So as I mentioned, usually we are taking to design a logical gates by these functionally complete sets of gates. So as mentioned, universal. So NAND and NOA such universal gates. So when we are designing a circuit, like we actually don't need to design such multiple gates. We don't need any AND gate or gate, not gate. Only we can design a circuit by using only NAND gate. So the fabrication will be very simple. You use only this type of gates. So it's considered about the functional completeness. Functionally complete sets. So one simply we can say and or and not. So this is a one functionally complete set. And so if you so and is A plus sorry is A dot B. And if you use in De Morgan's law, so this is about Boolean algebra, that is we are doing the double negation. So if you do double negation, the not going to do any harm. So it will be equal to this again. So not into not, but we can derive or we can it would be equal to it would be double negation, and we can derive this with by using only the De Morgan's law. That is A bar plus B bar into W. Right. So here there only we can see operation and is this not operation? Operation and not operation. Here and here. So what that means? That means not an O also another functional complete set. Also functional complete set. And we can do the same for the O gate as well. That means not and AND gate. AND gate will be also another functional complete set. And as I mentioned, AND gate and NOR gates also a functional complete set. That means we can do and this three operations and O and not using only these functionally complete set. That means only with using these two, only using these two, or only using this one, and only using this one. Right? Do you have any problems up to now? So show me the functional completeness of let's say not gate. No. So I have derived this A dot B. So derive A plus B also only using derive A plus B uh, A, C and gate and not. Let's do this. Derive A plus B only using A plus B, that means A or B only using and gate and not. So try to do derive A plus B only using and not. Okay, we got one answer from Sirini. We got the answers as well. Yeah, so thank you. That is a we need this as well. Yeah, that means A plus B double negation. Yes, A plus B. So we draw the yeah. Thank you, students. We draw the circle for this one. A B so going to not right. Yeah. Thank you, students. So let's do the same thing with name. Uh, uh, Only this game can derive any other game. So that means we can able to derive the not gate uh, not gate and gate and show, right? So I already explained that not operation will be this. A, also A, and here is A dot A bar. So A dot A is A. Here is A bar. So how we can derive the AND gate by using only AND gates. So simply I will do this way. So let's derive. Let's simply draw that AND gate. So here it's A B. This will get A dot B not, right? So what we need and is A dot B, right? If we negate this one, then we can simply get the AND gate, right? So how to negate? Again another AND gate. So this is here. F is A dot B not into A dot B into whole not. So we know is A dot B to whole A dot B, right? So here our F is A dot B. How to do the O? So O is A plus B. What we can do first, we need to remove this plus. Then you can able to simply derive the circuit. So simply we got A plus B double bar. So what is this? A bar, B bar, the whole negation. What we need A bar, B bar, and not. So there is A. So what is A bar? A bar can be derived by using not gates. This is A bar. So what is B bar? This B bar. And simply, so what is this? A bar dot B bar into not. So make sure to connect these parts. Very simple as it is. So here only NAND gates. derive the no gate. No gate only using using NAND. Please do this. Derive the no gate by only using NAND gates. We have answer. So put answer A bar dot B bar to double negations. Right. So what is actually not gate O gate OA or the O gate and no simple, right? Put another. So we need 1, 2, 3, 4. 4 and gates. So 1, 2, 3, 4. One A bar dot B bar into double negation. Is not by using only NAND gates. Right. So the next gate. No. So what we need to do is derive not gate, or gate, and gate. Gate by using only no gates. So it is the same, but this time we are using no gates. So try to type weights and derive the not gate, or gate, and AND gate by using only the no gates. So noise. So A or B do not. You can do only this operation. Yeah. For the time being, yeah, I think you can derive these ones. So it is same and previous. So this will be not. So that means A here A plus A below A. So we know A plus A is A plus. Okay. So simply B A plus B, and what we need to get O is A plus. So we need to have a negation. So what is the negation again? Another no gate. Plus B. So AND gate. It is out B. The name of A plus B. Right. So that is uh, negation. A bar plus E bar negation. Then AND, right? And try to draw these circuits by using only NAND. So I will quickly draw that gate. This is the NOR gate. Okay. So you can gate. Okay. Okay. So output is Q. So D will be A plus D. You know, E will be B dot C. And the output is A plus B not B dot C. So draw this circuit, draw the whole circuit by using only NAND gates. NAND gates. If we need to replace this NOR with NAND gates, and you need to replace this AND gate with NAND gates, and this O also with using NAND gates. Please do this quickly. Okay, I got one answer. So let's simply derive this one. D dot C using ANDs. This will be B dot C into naught, and we need to redo this again. So we have replaced the AND operation with using two NANDs. To replace no gate, right? We need to have O. So first this is no gate. And for this O gate, we need to have three NANDs. Right. So this is no, this whole thing is and this gate is O. And you can see this is double negation, right? Is again not 10, not. Let's say A bar and A bar. If we say we can remove these one, right? So that means we can reduce these two gates. And here also we can reduce these two gates because they are connected with each other and only doing the NOT operation. So double negation. So that means we can remove those two gates. So that means can simply connect these ones. So only we need 1, 2, 3, 4, 5 gates. So I think the answer of Sahan. Yeah, Sahan answer also correct. So how we have simplified? If we see double negation, we see this. There is double negation. So not this is also not. We can simply remove these ones, right? And even we use Boolean algebra. So in that way, we can get a reduced answer. So in home, please do the same thing by using no gates. Right. Do you have any questions about the today's session? So next week I will do Kanu maps about the Boolean algebra. So actually, we have gone through with these gates today and some Boolean algebra rows and using the NAND gates and OR gates. Yeah. From next week onwards, from next week I will told you about these ones, sum of product of sum, and simplified implementation and using column maps and the Queen Klansky method to simplify logic circuits. Right. Then we can go to the combination circuits, multiplexer, adder circuits, and decoder, binary addition, up to this one. Okay. Do you have questions? Or we can wind up the sessions. Okay, students, then we can wind up the session.